Okay, so in this video, we're going to look at partial fractions and revisit that. And, partial fraction decomposition is something that we looked at in logistical differential equations. And I like my little pun, we partially used partial fractions, right? But sometimes that might help us integrate, functions, especially if they are quotients. And we have other techniques for quotients. Like sometimes we might be able to use, a trig substitution or completing the square, and use inverse trig. But sometimes it may not be the most efficient, and sometimes you might not want to, like for example, if I'm going to complete the square with that 5, I don't necessarily maybe want to deal with the fraction, or maybe I realize, wait a minute, I can factor this, like x squared minus 5x minus 6. That's very factorable, right? So even though I maybe could use a inverse trig here to try to write this, and it might not because of that minus, right? That's the other thing too. Like even if you did complete the square, you might end up with like let's say like x minus like half of 5 over 2 squared. So 5 over 2 squared, but it might be a minus a number here, right? And so to characteristic format of arctangent would be u squared plus a squared. So here's again another method to look at, especially when you have a rational function like this, and maybe factoring might be very beneficial. So I'm going to factor that, and let's see. So it's x minus 6 and then x plus 1. And the way partial fractions work, is that you can think about breaking that down to the sum of its parts. So somehow that's equal to a amounts of x minus 6 plus b amounts of x plus 1. Because if you can find those amounts, then those are really easy integrals, right? Because you're literally just 1 over u, so they're just natural logs. So how do you find a and b? Well, so that kind of goes back to a little bit of HPC, what we did last, or even also last semester too. So I'm just going to look sort of not as the integral, but like think about, well, what if you had this function and we broke it down to its partial fractions, right? So in other words, 1 over x minus 6 times x plus 1 equals a amounts of x minus 6 and b amounts of x plus 1. So I'm going to clear the fraction. I'm going to multiply by the denominator. So x minus 6 times x plus 1. And what that'll allow me to do is work with a equivalent, but I think easier to manage equation. So when I multiply this whole quantity into the 3 different components, so to the b, to the a, and to the 1, because of our denominator, the 1 will stand alone. And then a times x plus 1 plus b times x minus 6. And so when I teach this in HPC, I remind students that there are 3 unknowns, an a, an x, and a b, but only one of them is a variable. Only one of them can vary, like the literal definition of a variable, like it could be anything. Where a and b are unknown, but they still are fixed constants. So if x is the variable, we choose smart x's to make our equation much simpler. So I might say, let's let x equal -1, because that would make that a 0. And there's no -1 to plug in here, so 1 equals basically 0. And then -1 minus 6 is -7, and then b. So 1 equals -7b. So basically b equals -1/7. And then on a similar note, let's let x equal 6. It's the other smart x, because that makes this value equal to 0. So then we get 1 equals 7a plus 0. So then a is equal to 1/7. Now, we sort of saw this in the logistical equations that often they are opposites each other. Not always, but often. And so when I'm going to now integrate, let's erase this here. So I can rewrite that as the integral of a, which is 1/7 over x minus 6, and then minus b, 1/7 over x plus 1. and like those are natural logs. And I'm, just as a reminder that technically you should be thinking about a u substitution for your denominator, because that's more than just a u, right? It's more than just an x. But because the coefficient in front of the x is 1, any assignment you make for the u, its derivative is just the x. So if you kind of understand that and see that, then you could jump right to say, okay, well then that's 1/7 the natural log of x minus 6, absolute value, minus 1/7 natural log of x plus 1 plus c. And, you could leave it like this. You could combine them. You could factor out the 1/7. It just happened to work out really nicely. There it is. Wow, that's the ugliest 1/7 I've ever seen. Okay. And then because you have a natural log of a difference, you could condense it to natural log of x minus 6 divided by x plus 1. Like I've seen that. On the AP exam, the 1/7 could come up as an exponent. But on a free response, anything equivalent would be fine. Okay. So, and then, the next one, partial fractions might be the only method because we have a cube here. So we don't really have anything that addresses a cube, but it does factor. So you have like t, and then you could say like 2t squared minus 5t minus 3. And then, you could factor further. So that would equal t times, then there's 2t, let's see, and a t. So let's do a minus 2 there and a plus 1 there. That will give you, oh, sorry, not minus 1, I'm sorry, minus 3, my bad. So that gives you -6, plus 1 is -5, and then -3. Perfect. So that's all over, or I should say all under 21. So now when I'm going to integrate this, I know that I'm going to have like 21 over t times 2t plus 1 times t minus 3. And so I want that to equal like a over t plus b over 2t plus 1 plus c over t minus 3. And, clear off our fractions. So, clear out the denominator. So we get an equivalent expression. So we get 21 is equal to a times, well, the t would cancel. So we get 2t plus 1 and then a t minus 3 plus b and then t times t minus 3 plus c, which would be t times 2t plus 1. And just like the last one, we pick smart values of t to help us isolate, right? Isolate, an A, a B, and a C. So maybe 0 is a good one. So let's let t equal 0. Now, nothing to put in this left side. So 21 equals. And notice I'm using this arrow because letting t equal 0 implies the equation becomes this. So I really don't need an equal sign there. So 21 equals, and then when t is 0, like that's going to cancel, and that one's going to cancel. So then 2 times 0 is 0, plus 1 is 1, minus 3 is -3. So a times -3. So it means, looks like, a is equal to -7. Then let's let t equal 3. And again, that implies that the left side is 21. Now, anytime there's a t minus 3 factor, that cancels. That cancels. So this is 2 times 3 is 6, plus 1 is 7. 7 times 3 is 21. So it looks like this one is coming out to pretty nice numbers. And then our last one, let's let t equal -1/2. Sorry, -1/2. Because that's going to cancel that factor and that factor. And so then we still get 21 equals. And then when t is -1/2, we get -1/2 times -1/2 minus 3. So that's -3.5 or -7.5. So b times -1/2 times -7.5, which would be actually a positive 7/4. So 21 equals 7/4 b. So when you come over, you multiply by 4/7. So it looks like that's 12 equals b. So now I'm ready to integrate. And now I'm ready to integrate. There it is. So a was -7. So we're going to integrate -7 over t plus b, which was 12, over 2t plus 1, and then c was 1 plus 1 over t minus 3. Now, as long as your denominator is a coefficient of 1 in front of the variable, you really don't need to use substitution. But what I want to be cautious of is that 2t plus 1. When I integrate that 2t plus 1, remember, that's going to need a u substitution. So technically, you should do a u substitution, 2t plus 1, but some of you are really good at these linear factors that you just realize that you have to bring that over, so it almost becomes a reciprocal. Because there's a 2 here, I'm anticipating that chain rule by making it a 1/2 for that antiderivative. So if you're comfortable with that, I'm okay with that too. So -7 natural log of t. So there's a 1/2 plus 1/2 times 12 natural log of 2t plus 1, and then plus just natural log of t minus 3 plus c. And certainly you could multiply 1/2 times 12. I wouldn't do too much more. -7 natural log of t plus 6 natural log of 2t plus 1, and then plus the natural log of t minus 3. So, and I mean, you could have this as for as many factors as you want, right? Now, what happens if you have a repeated factor, or what happens if you have a quadratic factor? So that's what we're going to look at next, in those examples.